Okay, hello everybody. We are starting this citizen science in a remote sensing context from examples to best practice webinar. This is a webinar organized by We Observe. We Observe is an Horizon 2020 project found by the European Commission. So thank you everybody for actually attending this webinar. We have prepared a program for you, just to inform everybody that this meeting is recorded, and we have a list of attendees and so on. If you do not want to be mentioned in that list, let us know. In any case, the meeting is well attended. We are very satisfied about that. There is a question panel that you can use. Actually, we have already a person that has tested the question panel. Thank you. We will read the questions and we will redirect to the right presenter in the appropriate moment. We have prepared 4 presentations for you. And a little bit of discussion. The intention of this webinar is to actually illustrate that citizen science can contribute to the Earth observation and even the remote sensing complementary technologies to actually create, a description of our environment that is fully comprehensive. So let's go ahead directly with the first presentation. This is from Linda. Linda is a researcher in the IASA International Institute in Vienna. She has been working on the PhotoQuest project. She is also participated in the GeoWiki before. After that, she also directed the project on the LACO-Wiki. So she's really an expert on doing platforms and projects that use citizen science for capturing land cover. So Linda, I will make you the presenter, and you will read your own presentation title. Let me see. And by the way, please remember to unmute yourself in order to hear you.
Okay, thanks very much. As Joanne mentioned, my name is Linda See, and I work at the International Institute for Applied Systems Analysis, which is a research institute in Austria. So I'm going to talk to you about a mobile app, a citizen science mobile app for collecting in situ land cover and land use data. We call it PhotoQuest. It's been developed by many people at IASA, so I've only mentioned myself here, but I would like to mention Dr. Stefan Fritz, who is also the PI of We Observe and the driver of this development, the app developer himself, Tobias Stern, and Juan Carlos Lasso Bias, who's done a lot of the statistical analysis. Okay, so to give you a bit of background, we know that there is a lack of in situ data needed for training and validation of land use land cover maps and other remotely sensed products. In fact, one of the only freely available in situ data sets is from LUCAS, so the Land Use Cover Area Frame Survey, which has been commissioned by Eurostat, and it takes place in the EU every 3 years. So what happens is that professional surveyors visit around 250,000 to 300,000 locations, so that differs from the survey to survey, and they document the land cover and the land use using a protocol. So they take a photograph at the location once they reach it. They take photographs in 4 cardinal directions away from the location, so in the north, east, south, westerly direction. And then, of course, they document the land cover and the land use, along with other information, such as the land cover changing along a transect, soil data, etc. So it's quite a complicated protocol, but we asked the question, can we simplify the protocol and engage citizens in collecting LUCAS-style data for complementing this survey. By complementing, we mean doing it, say, more frequently than every 3 years and spatially. So can we make a denser sample than is currently available in Lucas, and thereby increase the amount of in situ data which can be used for Earth observation and remote sensing purposes. Okay, so before I show you the app, I'll just explain that as part of the project, we had 3 PhotoQuest campaigns. So one was in 2015, and the last one was in 2018, with an intermediate one in 2017. But the significance of 2015 and 2018 is these are the years in which the Lucas surveys took place. So that means we could compare the data directly collected by the citizens with authoritative data from Lucas surveyors. Okay, so the campaign's different, and of course, the app evolved over time. That means we took on board feedback and we learned how to improve the app over time. So in 2015, we called it PhotoQuest Austria. So it was focused only in Austria, where we had Lucas points plus extra points, all spread across the country. We had a gamification approach in which people could do a quest. So a quest, I'll explain when you see the app, but it means going to a location, taking the photographs, telling us what the land use and land cover is. And for that, they would get points. And at the end of the competition, the person or persons with the most points were awarded prizes. The land cover selection was not super user-friendly, but it followed the Lucas protocol. And there was nothing to do with land cover change. So Lucas is all about change, okay? So it's about documenting change over time. But there was nothing in 2015. There was no near real-time feedback system, which I'll explain what that is in a minute. But they could communicate with us, so they could ask us questions. And we launched this through a massive media campaign. Then in 2017, we did an intermediate campaign, already taking on board lots of changes. And in 2018, we expanded this to EU countries. So it became PhotoQuest Go, also Go because of Pokemon Go, trying to take advantage of the developments in that area. And it was then PhotoQuest Go for Europe. We added a lot more training videos, so we understood that people needed to learn more about land cover in order to be able, and land use in order to be able to identify it. And we changed the incentives, and this is partly because this was part of a project to understand what incentives work with citizen science and crowdsourcing. So we changed the gamification side from points to micropayments, and I'll explain what that is in a minute. And we defined a much more user-friendly UI for choosing land cover. And we also added this change detection element. So in 2018, the players were shown pictures from 2015 and asked, has there been a change, okay, in what you see now compared to 2015? And then there's this near real-time feedback and quality control system, which I'll show you in a minute. Okay, so this is what the app looks like in 2015 if you had downloaded it on your phone. You'd be in Austria, and you, based on your GPS, you would see points around you. So blue points are points that have not been visited yet. Yellow points have already been visited, okay? And then as you approach them, they will tell you how many points. So you can see on the right-hand side that that point is worth 65 points if you go and make that quest. And then the GPS guides you towards that point so that you're close enough to be able to tell us what the land cover and land use is and take the photographs, exactly as in the Lucas protocol. And then, as I mentioned, at the end, the points are accumulated and prizes were awarded. Now, if we move to 2018, the interface has changed. We've moved away from 2D into 3D, so it looks a little bit sharper. And we've changed the incentive system. So now, instead of seeing the number of points available at a location, it's the money. So what happened is, for each location, we awarded between 1 to 3 euros. So 1 was the standard, and 3 was for points that were more difficult to reach, so further away from a road, all to do with accessibility. And then we also had these weekly challenges across Europe. So 1 random point was chosen, a Lucas point, and if someone reached it, they were awarded 30 euros. We also took advantage of the mobile technology. So, for example, the GPS obviously guides people to the locations, but we use the compass as well. So, as in the protocol, people would have to take a picture in the north-facing direction. So the compass would tell the user when they were in a north-facing direction, and then at the top you can see there's a big green button that would turn green if they were north-facing. They would then take the picture and move to the east and west and the south, and eventually take the 4 photographs and the photograph at the location. You can also see this horizon. It's hard to see on the top, but it's a faint white line, and that guides the user so that they take 2/3 land cover or 2/3 landscape and 1/3 sky. So we tried to use the mobile phone to help the users take the best possible pictures that they could. Okay, so in 2015, this was the land cover. It was quite basic, drop-down boxes. These are actually Lucas levels. So on the far left is the Lucas level 1, and then if they were to choose something from that list, they would go to Lucas level 2, etc. So you can see that that user has chosen grassland, and then a second level grassland without tree shrub cover. The other thing we added, which makes this useful for Earth observation, is this idea of the radius of land cover. So they were at the point, they look around and they see where the land cover changes. So for example, here, less than 10 meters. That means 10 meters around that point is grassland without tree shrub cover. So we actually have areas instead of just points, which makes it more useful for remote sensing Earth observation purposes. Then in 2018, things changed and the UI became a bit slicker, and we also tried to help the user through a decision tree choose the land cover. So for example, first they see very high level, water, bare land, built up, vegetated. If they were then to choose vegetated, they would see all the different vegetated categories. Then if they were actually at a point that was in cropland, they would be given cropland categories until finally they would be given the crop and there would be photographs. So that would help the user in identifying certainly crops that say that they're not familiar with. So I think that this visual decision tree helped a lot in identifying land cover. The homogeneity in 2018 was a little bit easier. Plus, we provided some visual guides, as you can see in the middle, a satellite image to give people an idea of what these distances mean. And then finally, the land use. There were 9 different land use classes, of which the user could select up to 3. Okay, so the interface did improve in 2018. And then I mentioned this near real-time feedback system, which we introduced in this intermediate campaign in 2017 and used in Anger in 2018. So the idea was, a player or a user would go out, do a quest, the information would come to us, and then we have a branch of GeoWiki called PhotoQuest Quality Check. So we would see, for example, where did the player get to on the map? Where was the target? And actually, where was the Lucas Surveyor? And sometimes the Lucas Surveyor was not actually at the point either, yeah? And then they would, we would be able to see what they chose from the decision tree in terms of the land cover. We would be able to see their photographs, and we would be able to say, yes, you've done a good job. You've identified the land cover correctly. Or your photograph is blurred, actually. Can you please take the photo again? And based on that, we would award them the 1 or 2 or 3 euros. Okay, so if we compare the campaigns in 2015, we had 76 players or users of the app. In 2018, 140. And then, as I mentioned, we moved from Austria to all of EU countries because Lucas exists in all these countries in 2018. And we had roughly the same number of quests done over those campaigns. Here we say 300 used for analyses and 700 used for analyses because those are Lucas points. So not so some points in the game were not Lucas points. So we tried to make points close to users. Otherwise, because Lucas points are spread quite far apart, and we wanted to make sure that there were enough points for people to gather information on. And again, this is this idea of increasing the density of points over the Lucas sample, and can that be useful for Earth observation purposes? Okay, so here are some initial results. So if you look at, this is just the agreement between the player or the user of the app and the Lucas points. Okay, so in 2015, you can see, for example, level 1. Level 1 is the really high level categories: cropland, forest, urban, built up. And there the agreement was around 70%, 69%, and by 2018, this had improved greatly. And in fact, you can see across all 3 levels, level 3 is the most detailed. There you're starting to get crop types. It had also greatly improved from 2015 to 2018. So we think, of course, that this decision tree with the photographs helps users be able to identify the land cover more accurately. And then using some statistics, we were able to show that the 2018 PhotoQuest participants were 2.9 to 3.5 times more likely to agree with Lucas compared to the 2015. So using the technology and also the feedback, we were able to improve the results. Okay, so some basic conclusions from that. Basically, improving the protocol and this visual guidance has resulted in higher accuracy in 2018 compared to 2015. And I think that the accuracy is actually good enough to be used, certainly the high level Lucas categories, for Earth observation purposes. This near real-time feedback allowed some degree of quality control, but really I think what it did is provide a sense of community. So we had given questionnaires to all the players at the end, and a lot of them really liked this constant feedback between us and them during this kind of campaign or the game. People are motivated to participate, but promotion and support is needed if you want massive uptake. So there I've shown you the kind of player numbers, but if you really wanted thousands and thousands to play, this would require quite a lot of promotion. But this was a research project, so this was just to demonstrate that it was possible. Also, what was interesting is in terms of incentives, prizes, points work, okay, monetary incentives work, but actually we also asked the question, you know, what's your reason for participating? And most people just said, it's fun, it's nice to go out, it's good to help science. We don't actually even care about the money. Mind you, they took the money, but the point is they didn't really care about it. So the incentive side is very interesting from a research perspective. And then finally, the cost analysis and full description of the 2018 campaign, it's still being undertaken. But I think overall, what we're seeing is that we get usable, high quality results that can be obtained for purposes of Earth observation. I mean, if you were to do a true cost-benefit analysis of Lucas versus what we've done, this would be interesting to see how much more cost-effective it could be. But keeping in mind, this is not meant to replace Lucas, it's really meant to complement the existing Lucas data. And then my final slide is just on the evolution of PhotoQuest. So during the various projects that we've been in, PhotoQuest, the backbone of PhotoQuest has evolved, and it's become part of other projects. So lacoviki.net, this is an online land cover validation tool. So here most of the online validation is done using visual interpretation and satellite images, but you can also send the sample you create within lacoviki, and this is a rigorous statistical sample, to the telephone. And it's the same principle as PhotoQuest. You would go to those locations and then you would validate the land cover or collect. There's different ways of collecting information about land cover through this mobile app. And then Paysage, this is part of the Landsense project. So Landsense is one of the citizen observatories, which is within We Observe. And the Paysage is again the same thing, sending users to collect information, in this case for the National French Mapping Agency. So here, for example, they have no information about the use of buildings. So they wanted to get that information to add to their authoritative database and send people out to collect it. And there's other bits of information that they ask the users to collect. And then other apps that have been built from PhotoQuest. So City Oasis, this again is a Landsense app for Vienna. And this is about, you can document places. This is more for urban planning. So I can say, this is a good place for running. This is a good place for walking my dog. This is a good place for relaxing, so that you can build up a perception of the city. Earn Data is part of a Restore Plus project. So this is all about land restoration, but actually it's collecting land cover and land use information. So again, useful for Earth observation. And then finally, FraQuest. This is FAO's Forest Resource Assessment. So this is an app to gather information on trees. Again, somewhat applicable for Earth observation. So PhotoQuest is evolving and becoming part of lots of different apps. Okay, so that's everything for me. If you have any questions, otherwise I think I should stop sharing now.
There is actually a question from the audience that says, on one hand, that your presentation was very informative, and on the other hand, how were you able to measure the accuracy in comparison to Lucas?
So Lucas publishes all the information. It provides the land cover and the land use at every point, and it provides all the photographs. So we requested that from Eurostat. You simply have to send them a hard disk, and they send you everything back. So we have the actual authoritative surveyed information at those points. Then we also have the data from the citizens, and we're able to simply compare those. So that's how we could do an accuracy assessment. So not on every location, so not on locations where we don't have Lucas information, but where we have Lucas information, we could do that. We could, of course, also look at the photographs that people submit and try to match that to the land cover, but we actually haven't done that.
I see. There is still another question related to the correct position of the Lucas points.
Yeah, sorry, I can't see the question. Can you read it? I'm just not seeing this.
You took the Lucas points as the correct version, but also note that some of the Lucas observers were not at the correct point. Is it possible that in some cases the volunteers were more accurate?
That's a very good question. We haven't analyzed that, but we could, because you could see that from the interface exactly where, okay, keeping in mind the GPS is an accuracy of say 10 meters on the mobile phone, but we could see where the Lucas surveyor was in relation to the target, and so you can see the difference. Sometimes, yes, we did notice that the player got closer to the point than the Lucas surveyor, but I mean, we haven't done a proper analysis of that, but we have seen examples of that.
All right, thank you, Linda, for your presentations. Some other questions are popping up. We will try and manage them afterwards.
Okay.
I would like to actually go to the next presentation. This is done by Valantis. Valantis is a member of the Smart Integrated Systems and Communication team of the iSense group of the Institute of Communication and Computer Systems. He has been involved in various European Union funded projects, emphasizing on the application of information systems in the environment sector. He's interested in SDIs, remote sensing standardization, environmental applications, citizen science, and crowdsourcing. So, Valantis, when ready, please tell us more about the harnessing of citizen science and remote sensing for improved environmental monitoring. Please remember to unmute yourself and to make.
Okay. Hello, everybody. My name is Valantis Tsiakos, and I'm a member of the Institute of Communication and Computer Systems, Greece. So I'm going to give a presentation about how citizen science, remote sensing, and novel machine learning techniques can be combined, leading towards improved environmental monitoring. In particular, I'm going to focus on the field of land cover and land use. There is a prominent need to include automatic assessment and monitoring of land cover and the state of soil in rural and urban areas, as well as to collect and detect seasonal changes, natural disasters, and human-related area development. So the traditional monitoring systems, such as Copernicus, produces a variety of valuable datasets relevant to environmental monitoring. This data is meticulous in order for the entire EU landscape. However, the update rate is scarce due to the increased cost and timely data validation procedures. To this end, citizen observatories, data and information can complement these official sources of information, allowing government authorities to improve and fill the gaps in the monitoring process. So the activity that I'm going to present, it is an output of the Horizon 2020 Citizen Observatory project called SEND. So SEND has created a toolbox that aims to extend repositories such as the GEOS by allowing for more frequent updates of local monitoring of land cover and use changes using inexpensive crowdsourcing tools. In the context of the project, and we perform various citizen science campaigns. The two main areas of focus were the Kifissos River Basin in Attica, in Greece, and the Danube Delta in Romania. So during these activities, different volunteers utilized the SEND toolbox. In particular, there is an application called SEND Explore, that it is basically an augmented reality game that allows people to collect information about the environment. In particular, I'm going to talk about land cover and land use. So, this information was used as the main training dataset for a map segmentation tool that we implemented. So one important element of the toolbox lies on the development of a machine learning-based automated engine aiming at creating maps that have well-defined region characterized and annotated with a predefined subset of the SEN taxonomy. So basically, the SEN taxonomy, it is based on Corinth. We just have enriched this a bit in order to include some elements that are needed for flood management. That was also one of the main focus of the project, how changes in land cover and land use can affect land management and monitoring. To this end, we used deep neural network technologies properly adjusted so as to implement this segmentation tool that aims initially to assign a semantic class based on the SEN taxonomy that I mentioned to each pixel. This means that we have to convert the raw data to a meaningful raster map. To convert the SEN taxonomy then annotated points into annotated areas on the satellite aerial maps, and to characterize whole areas for which a land cover use description is not available. Now, in terms of the map segmentation as a process, can be considered as an image or map tile or a pixel-wise classification task. And as such, we use an estimation techniques, and in particular, deep neural network technologies. So, in the context of the project, we do not have at our disposal fully segmented or annotated data examples in order to train our networks and perform pixel-wise segmentation, for instance, using the UNet or the SegNet architectures. So the major source of information, training data, is essentially a crowdsourced labeled GPS point coordinates, what we received from the volunteers that participate in the citizen science campaigns. So accordingly, image tile-based, let's say, classification is more suitable, considering the effective area around the GPS coordinates, as you can see here from the examples, labeled with the class specification of its sender. Now, just to give you a bit about the training data generation process. Here you can see an example from the Danube Delta area that we have our campaigns. So as you can see in the river, we have a few labeled GPS points that are shown with orange, red, and green field circles corresponding to ridge, forests, and shrubs. So a big challenge we face is that the labeled GPS points do not lie on the area characterized by the label. In particular, imagine that in the Danube Delta, all the crowdsourced points lie in the river since the volunteers were using their boats. Were using boats when going through the area. So based on this fact, the training data generation process involved several pipelines. The first step is to project the projection onto the area of interest. So as you can see, the initial step is to project the GPS points onto the riverbank, for instance, in the case, or into the roadside in Kifisos pilot area. When we're covering, let's say, elements about the riverbank and the river network, volunteers were in the sidewalk when we're taking these images. In order to do this and be able to do this projection, we use the gyroscope and compass information of the mobile phone. So as I mentioned, the application that the volunteers were utilizing, SEN Explore, was collecting the gyroscope and compass information from the mobile app, from the mobile device. And we use this in order to have a knowledge of the orientation where the volunteers were looking at this time, where they're taking the image. And also, in order to perform this projection, we utilize the texture differences between the river and the riverbank. So after this, as you see, we perform what we call a label propagation. So for all the labeled GPS points, a square title can be defined, center of the projection point. So in our case, imagine that we have 64 to 64 pixel squares. And such tiles were utilized as training data in our classification model. So due to the limited data availability, you can see, it is necessary to propagate the labels looking for neighboring GPS points, meaning satellite map pixels, which are highly likely to correspond to the same class. To succeed in this, the projection points were propagated along the virtual lines corresponding to the original GPS points and the projection points. So the propagation can be achieved as far as the texture that you can see here, the information about the texture and the local virtual lines is defined and allow us to do so. And through this distance, the virtual lines, we do some sampling in order to obtain more tile classes. So this is an overview of the different, let's say, data collected in this massive area in the Danube Delta. And it was utilized in the context of this training. As you can see, because the volunteers were moving along the challenge during the activities in the context of the campaign, so we don't have information and the needed information, let's say, in the middle of this area. So this is why this label propagation process was really important. On top of that, we performed also an augmentation process in order to combat the limited diversity of the label tiles. So in particular, we did some affine transformations, random rotations, and color jittering in order to increase tenfold the available training data for this. Here also you can see some examples of the data tiles about different, let's say, land cover types that were of interest in the context of the project. Here also you can see an overview of the deep neural network architecture. So this is inspired by the VGG16 network, comprising at the same time custom elements to increase the focus and attention of the network to the central area, as I mentioned, of each tile. So this allows us to have enhanced segmentation performance along the edge also of the neighboring classes. And also the fourth channel, as you can see here, corresponding to the rear infrared, has been incorporated into this model. For this, we utilized Keras with TensorFlow in Python. Now, the training strategy for the deep neural network involves an initial, a two-stage initialization process for transfer learning. The initial way was set to the VGG trained or ImageNet. And then we have also a second pre-training stage where the neural network was retrained based on an extensively large collection of open data tiles that are relevant to the land cover land use classification problem that we focus in the context of SEND. And after the pre-training stage, the last 6 convolutional layers and the fully connected part were retrained using the SEND training data tiles. And after this, the initial step is to perform the actual classification. It means that the trained deep neural network model has to be applied to all possible overlap tiles of the satellite maps, and also each pixel and the center of each tile is classified to one of the segmentation classes of interest. Here also you can see some of the results. This is an example of the land cover map produced in the context of Danube Delta. And also here I have included some of the highlights, just to see visually what is there and what, let's say, was achieved, the detail in this process. Okay, so and further to this, just to conclude the analysis, we performed an analysis conjunction also with Corinne data for the area. So here you can see an example for the Kifisos area in Greece. So basically, the thematic, let's say, classes that we consider for this, it is bare soil, cultivated areas, forests, and artificial areas. So these thematic layers have been generated considering the level of diversity of the annotations provided by the volunteers in the context of the campaigns, as well as the requirements of the hydrological models in terms of land cover information and points of interest defined. For instance, for Kipisos case, we need land cover information to define how pervious an area is, meaning how much water is entering the soil. This subsequently for flood modeling that we also examined in the project, it is used to characterize how rough the surface is. So here you can see, and in order to facilitate this analysis, we perform, as you can see here, an aggregation of the Corinne classes so as to establish a thematic consistency. Also, these three images in the top of the screen, so they show the first one. It is a part of a World View 2 satellite image. So we used World View 2 and Pleiades images in the context of this, because we understand that the analysis of the data that we have to consider and the microstructures that we need to take into account the context of the project requires very high resolution data. And so in the left, it is a part of the World View image, number 8. This is located upstream of Kipisos River Basin. Now, the second image in the center, it is a Corinne land cover map of 2018 for the same location. As you can see, it is characterized as discontinued urban fabric and complex cultivation, the yellow. And here you can see the detail that we are able to, let's say, to achieve through this tool. Okay, having artificial areas, bare soil with brown, cultivated areas with purple, forest with green, and so on. And yeah, so and here also in the statistical analysis, you may see that the biggest, let's say, disagreement between this map and the Corinne, of course, lies. Okay, it can be attributed to the spatial resolution of the two maps, but it is shown in the cultivated areas. So in principle, we saw that in some cases, in most of the cases in Corinne, and also in the artificial areas. So in Corinne, usually the artificial areas are following a visual inspection. You can see that they cover also bare soil, cluster of trees, shrubs, vegetated areas, and so on. And also this can be expected due to the minimum mapping unit in Corinne. But since here we are able to achieve some more detail, you can see the difference between these. And also similar analysis, preliminary analysis again with the Danube Delta area. Here you can see also an example for this. So this is a Pleiades image for an area in Danube Delta. Here, all this area in Corinne is characterized as inland marsh. And here you can see more details about the classes that we achieved in the context of this. So this is it, and thank you very much.
Yes, thank you, Valantis. This has been the second presentation about how we can use citizen science to improve land cover and land use maps. And well, I don't see, there has been some activity and questions in the question panel, but I don't see any particular question formulated to this presentation of yours. Maybe the question is how this methodology that you are presenting here could be operationalized in support to the creation of better land cover maps.
Yeah, you know, this we did this utilizing data from two, let's say, diverse environments. One, it was in the case of resource, that it is quite an urban area, and the other one was in the case of the Delta, more a rural, a remote area. So from where we collect the data. So if we, let's say, we adopt a common taxonomy like the one we have also for the CORIN, or even if we want to extend this and be able to collect, to have, let's say, from the citizens this information, this crowdsourced data, we could further, let's say, retrain the model so as to be able also to recognize other, let's say, classes of interest and produce full maps of an area. Okay, as you know, this process depends purely on the data provided by the volunteers. Okay, so if we could have, let's say, information, have citizen science campaigns in various areas or in other areas, this could allow us to extend this and make it applicable to also to other areas of interest.
Thank you. We are going to the third presentation. There is some interest in getting the actual slides for downloading later. Let me just inform you that both the recording of this meeting and some of those presentations will be made available. The GoToMeeting system will allow us to send you a concluding email with those materials. So Mel Woods will give us another presentation, still touching the land, but this time to see if there is some moisture in there. She is chair of the Creative Intelligence at the University of Dundee. Is part of the leading team of the project Open Design of Trusted Things. This is an European research project consortium that provides training to a group of future researchers and leaders capable of operating at the intersection between technology, society, and policy. She has been involved in other citizen science projects funded by the Commission, like the We Observe and the GROW Observatory for Soil Moisture Monitoring. So Mel, when ready, please proceed.
Okay, so first of all, I have to apologize because it seems when I switch my presentation to play, nobody can see it. So we're going on the view that you see at the moment, and of course we can share slides, and we also have a full paper on the presentation that I'm showing you today as well. So I'll proceed. So my name's Professor Mel Woods. I'm working with the University of Dundee and in the lead team for the GROW Observatory, which was a citizen observatory looking at sorry, yes, here we go. Looking at a ubiquitous soil moisture data set in order to attempt to validate Sentinel-1 products using crowdsourced data for a commercially available low-cost product, which was the Parrot Flower Power app. Flower Power sensor. In addition, what we were hoping to do is build up communities of practice, and that is engaging with growers and farmers and others who are working the land every day, who would take responsibility for the sensors, and who would in fact start to, when data became available, use data for themselves for their own management of the land and soil. So in effect, we were hoping to support a movement of citizens generating, sharing and using data and information on growing and land practices. And this was to address urgent climate challenges for science and society. In effect, one of the really key critical aims was both to gather this ubiquitous soil moisture data set, but also to make that highly relevant to citizens in different geographies in different parts of Europe, so that soil moisture data set has a different prominence and value for those in the Mediterranean who are experiencing drought, wildfires, etc., in their growing practices, than it is for a community in the north of Europe, in Ireland, Scotland, and in other areas where flooding and other different and related soil moisture related practices are important in order to create food sustainability and to manage the land in a way that's in the way that they want to. So the soil moisture, of course, we know is a pivotal element regarding water, energy and carbon fluxes. We know it's key for land use and food production. Monitoring soil moisture is challenging because it's highly spatial and temporal variability, even within a single parcel of land. And in the last decades, microwave sensors on board satellites have proven the capability to estimate soil moisture globally, but that is an estimate. What we were hoping to do is to get a much finer grained understanding of that using crowdsourced sensing. So the background to the soil moisture sensor we're using, which was the flower Parrot sensor. It's a commercially available sensor at scale. At the start of the project, we invested in buying 15,000 of these sensors to distribute across Europe to specially selected sites. And one of the first things we did was to validate this low-cost sensor both in the lab and in the field. The performances of sensors were thoroughly investigated in terms of soil texture and type, ranging from sand through to clay, and in the field next to official monitoring stations. And we proven there in Xavier's paper, which is available for you, for a strong consistency with the gravimetric samples. And you can read a little more about that in that paper. So this is an image of the sensor itself, showing the variable data that it's collecting: sunlight, temperature, conductivity, and of course soil moisture. We were most interested in the light, temperature, and soil moisture with respect to the types of land cover and land use that was going on in and around the sensor for which we were collecting soil moisture. So background validation, of course, the validation of remote sense products is a crucial step to understanding their reliability. The most accurate reference data for the validation purposes are in situ. However, installing and maintaining the ground sensors is really expensive and time consuming, and there are few sensors available globally, and they're unevenly distributed. We developed the GROW approach, which you can see probably vaguely here, given the view you've got of my screen, which was a 7-step approach that guided all of our activity through to scoping the challenges, the engagement of stakeholders and the building of community, which of course is highly important if we were to achieve a longitudinal data gathering, continuous data gathering success. So discovery, so we were exchanging knowledge and training our participants using massive open online courses, attracting altogether, I think we trained highly engaged over 20,000 people. And we then went about sensing, to place the sensors and to follow specific protocols that were designed by scientists. We had an awareness raising training as well, so that both scientists and the participants could use the data for themselves, thus creating a virtuous cycle of citizen data use and scientist data use, and therefore supporting this continuous monitoring. We had innovation on the data too, and then at the end we moved to an advocacy stage where we went out into the community and into policy in order to share our results. So that guided our development, with the values of empowering, collaborative, open, and impactful were our values that we stuck to. So essentially we were turning data and knowledge into change practices. We really wanted to know how our citizens were actually using the data for themselves. We opened up our data sets, the raw data sets, and we found that farmers and others began building platforms and building their own monitoring capability for themselves on their farms and within their communities, and began to use the data in all sorts of different ways, which I'll come back to later. Essentially, we had a site definition for GrowPlaces, 24 sites altogether throughout Europe, and you can see a map of them here. And we had both scientific and social criteria in order to select our sites. So meaningful geographic coverage across the breadth of climate, soil and land use types, and agro-technology approaches. So from larger farms and community farming down to those that were interested in permaculture, etc. We had an area of approximation described within the protocol, within the distribution sensors of about 1,000 sensors. The soil, terrain and land use variability characteristics were looked at, and we had to have a good quality of environmental data, so terrain, soil and land use. In order to also support this continuous soil moisture gathering, we had to have social criteria as well. So our sites had a scientific institution capable of supervising the process in order to ensure data quality and robustness, a local organisation with an established connection to maintain and extend the network. So often these were existing communities and with community champions, and the identified community champion who had competencies, leadership, education, ability to test the engagement and awareness raising strategies and tool sets. And they also supported, as well as the online training, they supported face-to-face, a blended training approach, so they could monitor how the community was doing on the ground. Our low-cost sensor, we designed our protocol for the minimum observation to be a period of 1 year, which meant that sensor was continuously in the ground for the full year. It posed all kinds of problems when it comes to farming practices and managing the land, but that's for another presentation. We had sensors that were located in areas that were unreliable, and these were removed from the data set. So urban areas, forests, or in close proximity to water, these were excluded. The measurements had to be flagged as good in this international soil moisture network quality control. Measurements taken with air temperature of less than 4 degrees were also discarded. And you can see here we've got an image of the distribution of in situ sensors that were employed for the temporal analysis. And comparisons also were taken with other satellite soil moisture products, and we can see this if you can see this in the slide here. So data and methods, the pre-processing and analysis, the temporal matching, there was an in situ observation that were closest to the satellite overpass for each individual product which was considered. There's a scaling. Pre-processing for satellite observations were rescaled to a mean standard and in situ measurements to account for systematic representation as error, and different depths were sensed and different measurement units also. And then there was also statistical metrics too. So we analysed and intercompared the temporal consistency of the various products, employing data from 154 ground sensors covering different climatic and environmental conditions in Europe. And for those of you who are interested, this sample data set is now available on the International Soil Moisture Network database for further interrogation, and you're able to download that data set in order to interrogate that further. For the project as a whole, because obviously this was a subset of sensors that we used, we had by the close of the project over 6,000 sensors placed and returning data. So the sensors that this study was built on was a much earlier subset of sensors that had already achieved more than 1 year placement in the ground. So a whole season of placement in the ground, and that included winter seasons, where in some places, in such as Poland, our sensors were in the ground at in frozen conditions up to -25 in temperature. So you can imagine some of the issues. As a result, and the whole of the whole project, we produced some visualizations that allowed our citizens to interrogate their sites. And here you can see one of the soil moisture maps from one of the Scottish sites, showing the overarching view that could be scaled and moved in and investigated per sensor, the moisture, light and temperature, which were dynamic maps which could be scrolled over. And here we also have some of the other activities that our individual grove places engaged in, using sensors and open soil moisture data to inform wetland monitoring and water resource use, wildfire mitigation and disease monitoring. And these were just the ones in the Mediterranean region. So for the results, we analysed and intercompared the temporal consistency of a number of products with Sentinel-1. The data from 154 ground sensors covered the different climatic zones. Our results confirm that SMAP and ESA, SSI, SM performances are comparable, and they're generally better able to capture the soil moisture dynamics of compared to other product. And well-represented satellite pixels, i.e. those monitored with high number of in-situ sensors, we found that a wide range of satellite products' accuracy were dependent on the individual center and the reference. And for well-represented satellite pixels, i.e. those that had a high number of in-situ sensors, we found a wide range of satellite products' accuracy, which was obviously dependent on the visual sensor used as a reference. And it's more prominent for coarse scale products. However, the same behavior was observed also for high resolution soil moisture products. Moving on, our results also suggest even at kilometric scale, one single in situ sensor might not be representative of the overall soil moisture dynamic, but it's valid for highly fragmented landscapes. So there's the presence of various land cover types, obviously leading to greater variability of soil moisture spatio-temporal patterns. The use of crowdsourced observations we think is of utmost importance, because it allows us to monitor soil moisture extensively at the subpixel scale, reducing representativeness errors and uncertainties generally associated to conventional networks. Our results, we think, are highly encouraging, and there's implications for the design of COs and the integration of CO for Earth observation. Most noticeably, social aspects play an important role in creating opportunities with the remote sensing community for environmental monitoring. This requirement of continuous monitoring is a high bar to reach. It should be determined over an extended period of time, e.g. months or years. And there's an ongoing need for strategic approaches to both the development of scientific protocols and criteria and the engagement of resilient communities of practice and place. And finding a balance between scientific requirements, selection of sites, interest and locations of citizen scientists, and varying technical and social competencies point to the needs for training and support. However, there was a huge interest in this, particularly in the release of the data to the communities themselves. And the project has recently released a new app which bypasses some of the services that had to be reneged at the end of the project, and we have a number of our sites continuing to monitor. So we will be updating the International Soil Moisture Network data set with many more sites and many more sensors that have a longer temporal consistency. So this was the first experience using crowdsourced measurements for validation of remotely sensed soil moisture, and these are our results there. I have to say that obviously you'll probably be able to tell that I'm not the scientist that was involved in the work. I was the one who designed the overall model for the observatory with the engagement strategies and the social engagement with the communities. However, we do have all of the results in the full paper that we've submitted, and that should be coming out in a matter of weeks. So we'll be delighted to share that with anybody who's got a specific interest in those results. So thank you.
Thank you, Mel. your presentation has awakened some interest in the questions panel, in particularly one spontaneous reaction of one person that says, "Please, yes, I need this paper." There is another question about extending the project to other continents, in particular to Australia and Africa, different soil types. Sorry.
Yeah, so we I mean, with the release of so we've got a new Android and iOS app. I think the iOS is imminent, and a new cloud database, which is at University of Edinburgh. We're ready to go with that at the moment. We've been looking at low cost open source sensors and have tested a number of those out at the end of the project in order to replace the flower power sensor. So that's our next step, essentially. And yes, and we think it's got a high degree of relevance to the countries that you've identified, and there's a huge amount of interest, and still the team is working together. So we'd be certainly interested in replicating that in other parts of the world. We recognise, and we did a test also with the flower power sensor and its mean life. So we had a mean life cycle for the sensor of 18 months, which is actually pretty good when you look at the average of a low-cost sensor for continuous monitoring through a range of conditions. But that is a test that we would have to do with, and the validation tests, obviously, with any new sensors that we brought on board to the platform.
Yeah, there is also a question of related to the reliability of the sensors, but I believe you already answered that. It was at the beginning of the presentation that said how many of these 15,000 sensors are still measuring. You have been commenting about the reliability and durability of those, so maybe that's already answered somehow.
We have kept, I think we have something like a stock of 300 sensors kept back, along with some of our other sites have some sensors in reserve. So quite often one of the issues with the sensor was the housing. That seemed to be the thing that failed in these weather conditions, and also farming practices and sheep sitting on them and all sorts of things. So sensors were replaced as to maintain the monitoring over time. And so we still have a very small backlog of sensors, and also to do a comparison with any new sensor that we bring on board in terms of the validation. The validation in comparison to the flower power and in comparison to the official monitoring sites that we've done the initial validation tests against.
All right, thank you very much. So and now I have the responsibility. I'm trying to make myself the presenter. I have now the responsibility to present myself. And I should say, for instance, that I work at CREAF. That's a research center institute in Barcelona. I should also say that I could define myself as an activist in standards for geospatial technologies in general. Well, I have been engaged in several projects related with citizen science and visualization technologies in general. And I'm the chair of some kind of interoperability guerrilla that we have here, and we observe that, but we don't call it that way. We call it the We Observe Interoperability Community of Practice, with the focus on actually improve the interoperability of the different citizen science projects in order that they are able to share data and data seen together and being compatible with other sources, things like that. And well, I should start presenting remote sensing as a driving tool for citizen science phenology monitoring campaigns. And I will start by saying that, I mean, there are some rhythms in nature. There are daily rhythms, of course, but what we are talking about here is about the seasonal rhythms. Plants actually reflect those rhythms very well. Animals also have rhythms in migrations, in hibernation periods, things like that. But the important thing here is that those rhythms are actually driven by internal factors and environmental factors. And those environmental factors are actually impacted by climate change. So phenology becomes an indication of the climate conditions and also an indication of the changes on these climate conditions in terms of, you know, movement of the flowering, breeding, and so on, exact dates and periods. So that's exactly the definition of phenology, and it has become one of the climate change for European policy indicators. We are seeing in Europe that leaf unfold is up to 1 day earlier every year. So that's a lot because there are so many days in the year. So in the end, if we project that in tens of years, we are going to see even seasons disappear. So what we did in phenology in the past was a traditional monitoring system, sometimes even going more than a century ago for a particular species, like you know, so some fruit trees and so on. This monitoring was done in paper, required a systematic and painful effort. So it covered a reduced number of species. There weren't so many observers, and they were relatively close to home. So they didn't represent the totality of the picture. Nevertheless, there are some phenology monitoring networks available. There is one European that I'm mentioning here, the Pan-European Phenology Database. And there are local or regional phenology networks like the PhenoCat. That's an initiative from the Catalan Weather Service. In the context of ground truth, we proposed one citizen observatory that actually measured phenology, and we start building on top of what existed in Catalonia. The name is Ritme Natura, translates literally to nature rhythms, and well, the data was stored in a biodiversity platform with small modifications for phenology. We are monitoring 12 species. I mean, the idea is to have real-time searchable data for scientists, management, and policymakers, and to correlate those effects in the phenology with the climate change. But of course, this is a long process because you need long time series to do that. I mean, the thing is how we could improve the number of observations. The answer is precisely using citizen science to do that, and this is precisely what we did, at least in the Catalan region. But you know, this still is limited to a relatively short number of species that are easy to identify, and they are visible. Their changes to naked eye. How we could extend that to make it more, you know, consistent and comprehensive is the use of remote sensing. But the problem is, you know, what is done in remote sensing is kind of a different, because as you can see, the optimal sensors are the ones that have daily data, because you need actually to see this change in the particular day that this happens, like a flowering or something like that. So even if they have the ideal spectral configuration, you see what happens in the map. I mean, it's so blurred, the resolution is so coarse that you have more than 10 in a pixel, so you only have an indication of what is happening there, but you are not observing exactly the same as if you were in the field and you were observing species. If you go for satellites with higher resolution, with the hope to be able to do that with more detail, you have the problem, or you had the problem in Landsat, that the revisiting period was too low. And if you have 16 days and clouds in the middle, you really miss your opportunity most of the time. But with the new constellations of high resolution orbital satellites, it seems, the European one, Sentinel-2A and B, it seems that the revisiting period is becoming so 3-5 days. You will indication of when the exact phenomena happened and if there has been some change between years. And this is going to provide you with global coverage, so that should be excellent. So what we see in the ground is something like this. We have a tree and we see some flowers here, and what it could be really great is if we were able to actually have some patches where there are many of those do I? Okay, sorry about that. I believe I got somehow disconnected from the network. And since I'm back, I will continue. I was just saying that you know, if you are on the ground, you are seeing something like this. You see the flowers one by one. What could happen if there were many of those trees together, and you had some kind of homogeneous patches that are big enough? So in principle, that should be able to be visible from space. And if you try it in that particular spot, you really see changes in the color of the image that reflects the status of this particular field. So no doubt that there has been flowering here. But to do that, you really need to combine your knowledge of the land and with what is the habitat on that land, what is the dominant species, and then you will be able to actually see something that is useful. So just analyzing the time series of the different colors captured by the satellite, you are immediately able to detect here in the red that there is a peak. This is the flowering season that you were looking for. So definitely that can complement the observations from the citizens on the ground. So the phenotype approach is really about knowing where these homogeneous habitats with dominant species are, and trying to direct the volunteers to those places. And we have a map where people can go. They find out where are those places. They have a GPS to actually go to those places and then provide us with information of what they have seen. So the whole idea is to actually being able to automatically to demonstrate that automatically remote sensing observations could be made compatible with in situ observations only in patches where there is some homogeneity. There are many of them because Sentinel pixels are relatively small, so you don't need huge extensions with homogeneous species. So that is possible, and we are using citizen science observations to actually validate that what we are seeing with remote sensing is correlated with what a citizen scientist on the ground is able to see. So in conclusion, remote sensing can provide the spatial, temporal, and spectral resolution suitable for vegetation phenology monitoring. And we can complement the in situ observations with remote sensing in homogeneous areas to monitor the phenological evolution of a single species from space. So citizen scientists can be directly directed to these homogeneous patches to observe the phenological changes as necessary to complement and validate and improve the methodology we are doing, and also maybe to extend that to other non-homogeneous areas. So in summary, remote sensing and citizen science have a good partnership for phenology monitoring, and that's why the project that we are conducting to demonstrate so is called PhenoTandem. So thank you. And now I have to find out if I'm still online or not, and if there were questions in the panel. And I apologize, and I have to apologize for the interruptions that we had. So this is the end of the program we had. Maybe we could use the question panel to actually discuss a little bit on what we have seen. If I'm able to find the question panel, this is my issue now. Esther or Valentis, can you help me on this?
Hi, Joan.
Hello. I have lost my question panel, so I should try and find it. During the disconnection, the question panel disappeared from my view.
Well, it should be under the chat panel, but there is only a comment about a very interesting presentation, Joan. Thanks a lot. And then there are still a couple of questions for Valentis. How can you manage the overlap information? And it brings different information length cover, for instance. This is for Valentis. And another one, why are you doing it with people and not with drones? Also for Valentis.
Okay. In terms of the second, covering such vast areas with drones, it is not that feasible. In Danube Delta, as you see, it is really a vast area of hundreds of square kilometers. So, and also the cost is quite high in order to achieve this with drones and cover this area. We use drones in the context of the project for aspects. I mean, we use it also to check blockages in the canals and some things like this. But a wide mapping of the area. It was not, let's say, an efficient approach to proceed. So this is why we used data from the Copernicus contributing missions, meaning Pleiades and World 2. And regarding this, just as a side note, we have also tried to enhance the overall segmentation performance by simultaneously considering not only the very high resolution satellite data, but also to fuse in the model data from Sentinel-2, in order also to exploit the wide spectral information it provides. Unfortunately, although this fusion led to some improvements to classes that occupy wide areas, such as lakes and land masses, for instance, in general caused an observable reduction in resolution, delineation of microstructures, such as the riverbanks and the strands and so on. Therefore, such an approach was not adopted finally. Now, regarding the first part about the overlapping, it was basically all it came. It was through the square tiles that I showed in my presentation. Okay, so we didn't experience. We don't have any issues, in terms of the sampling process. If this is what you mean. Also, currently, we are compiling a paper regarding this, and it will be published. But we will have also details. But if you are trying to do something similar, also in the case, we would be happy to interact with you and exchange views about how it could be done. Thank you.
All right. So thanks everybody for being here. The objective of this webinar was actually starting this process that the second part of the title says, from examples to best practices. So we are collecting these examples on how citizen science and citizen observatories and remote sensing can work together. Our objective is actually to extract lessons for this, and eventually to work with the Copernicus in situ segment in formalizing some pilot where citizen science definitely demonstrate that can contribute to the elaboration of high-level remote sensing products that are the ones that the Copernicus services and the Sentinel fleet are providing for the whole Europe and beyond. So, well, you have participated in this part where we are presenting these examples. The We Observe project that you can find at the www.weobserve.eu will continue this work by defining this pilot and presenting this pilot as one of the best practices to make this interaction even more existing, that what we are really doing that. And those that were presented here are just examples, and probably there are many more. So thanks. I have to thank the presenters, Linda, Balantis, Mel. I have to thank the 45 attendees that has maintained the attention from the beginning of this webinar to the end. And as I said, if you are more interested in what we are doing, please go to our website and you will find out more. Thanks, everybody.